So at last lesson, we were having a look at instantaneous rates of change. And we saw that we could estimate an instantaneous rate of change by looking at the average rate of change over a very, very small interval. So I'm going to look at this again, but in a slightly different way to sort of start bringing us towards the idea of being able to define an instantaneous rate of change. So just to remind you, the average rate of change was f of b minus f of a over b minus a, where a is the x coordinate, x1, say for example, and then f of a would be then the y coordinate. So what happens when I replace a x with a in the functions equation? B is a little bit further on, and it's like x2, and f of b is like y2. Okay, going to change the language around a little bit to help us understand the next bit. So let me just go to Desmos. And you can see here that I've just got your old pal f of x equals x squared. So classic kind of equation here of a quadratic. And I've got a point here which is x comma f of x. Now you don't have to understand any of this here, but I'll just unpack a little bit. You can see that I've got a coordinate 2 here, which means that f of 2 is 2 squared, which is 4. So x comma f of x would be 2 comma 4. So that's like a and f of a. And this is like b and f of b. But rather than putting it in terms of b and f of b, I've said, well, let's call b x plus a little distance, which we're calling h, for a tiny distance. Okay, so if x plus h is the new coordinate, then f of x plus h is the is the y coordinate. I just realize I haven't quite written that correctly, but there we go. Quick fix. So x plus h is the x coordinate. Substitute x plus h into the function, and you will get the y coordinate. Now, if you're a bit shaky on transformations, this might look a little bit scary, but it will be unpacked as we go through today's and next lesson. So don't stress about it too much, but just get a sense of this is the x coordinate and this is the y coordinate, which is just a little bit further on from our one of our points. Okay, so the reason why I've got it set up like this is we're going to focus on h. And we can see that h is equal to 2 here at the moment. So if x equals 2, then x plus h is 2 plus 2, so it's 4. So f of 2 is going to be 2 squared, which is 4. So that's 2 comma 4. So I don't think I can show you on this, but you can probably see it from the coordinates 2 comma 4. And this one here is the x coordinate is 4, 2 plus 2. And so the y coordinate is f of 4, which is 4 squared, which is 16. 2, 4. So, and we can see that the chord here is, in terms of approximating the graph, it doesn't do a very good job. There's quite a big gap between the two, and therefore the gradient of the chord, or if you like, the gradient of the line, the secant, is not a very good approximation for the f of x equals x squared. What I can do though is I can slide h down so it's a smaller value, let's say down to h equals 1 all the way down here. And as I slide down, if you're looking at the graph, you can see that the blue line is now getting closer to the red line, and therefore its gradient is a better approximation of the red line over a shorter distance, of course. So that's h equals 1, for example. But although you can't see that there's much of a gap here, really, because we can zoom in on this, we can readily see that the gap sort of starts to widen once we zoom in a bit more. So the gap is definitely there. Is still an approximation, but we can still keep shrinking. I might just get this out of the way now. We can still keep shrinking the gap between x and x plus h. So remember, what we're doing here is we're bringing the x coordinate and the x plus h coordinate closer together. Okay, so there's less difference between the two. And we can bring them really close to each other, and now they look really, you'd think that this blue line would be a good approximation of this part of the graph in terms of gradient, and you'd be right, it would be a pretty good approximation, but it is an approximation. And I can keep bringing it closer and closer and closer and closer until it does look pretty good, like so. I'll just zoom out so we can sort of see it really does look good. But it is still touching the graph at 2 points. Okay, so it's still not an instantaneous rate of change. It is still an average rate of change over those 2 points, even though those points are really, really close together. So what we want to do is we want to keep on shrinking that distance. Okay, so I'm going to keep shrinking that distance a little bit closer, a little bit closer, a little bit closer, and it's still looking pretty good, right? I mean, if I zoom out enough, they pretty much look like they're on top of each other. So you'd think that would be a pretty good approximation of the instantaneous rate of change. If that was, say, 2 and that's 2.01, then you'd say that the gradient of this secant line here would be pretty good. But it's still not exact. It's still just an approximation. So we need to keep on moving it further and further, or closer and closer together. And we could do this forever, right? We could make this one 2 and this 2.0000001, and then work out f of x or f of 2 and f of 2.00001. And that would still give us a secant line. It would still give us an average. It would not give us the instantaneous rate of change at 2, but it would give us something which is pretty darn close. So what's the logical thing to do? What's the logical thing to do if we want to make, if we want to get rid of this secant line, if we want to make it so that this line is exactly the gradient of, say, 2, x equals 2 and f of 2, then what we need to do? You might want to pause the video, talk about it with the person next to you, maybe, if you want to, or think about it. Whether you pause it or not, we'll keep moving. I hope you can see that probably the most obvious thing to do would be to actually just keep on sliding it until h was 0. Because if h was 0, there'd be no gap between these 2 points. And if there's no gap between these 2 points, then we would say the gradient would be at that point. So I'll slide this to h equals 0. I mean, you can see it here if you like, if it's easier. It's got h equals 0.03, 0.02, 0.01, 0. Great. But then we run into a difficulty. That secant line has disappeared. Why has it disappeared? I might want to pause the video in a second and think about why it's disappeared. And the answer to that is when you think about the gradient formula at this point. So pause the video and maybe have a quick discussion about that, or a bit of a think if you don't want to discuss it. Okay, did you ever think about that? Let's have a look at this. Maybe this might help you understand what's going on here. So I'll just go to Air Sketch, and what we've got here really is this idea here that we've got 0.1 is like x1 comma y1. That's like 2 comma 4 in the example we had. 0.2 was x plus h comma f of x plus h. But then we let h equal 0 because we slid it all the way back to 0, which means that this is just going to be x and this is just going to be f of x because h equals 0. So we've got this idea here. If I've got 2 points, but so the gradient is therefore this, rise over run, just the usual. But if x2 equals x1, in other words, if these two coordinates are the same, so with these two, but that doesn't matter. If these two coordinates are the same, what are we doing down the bottom here? What are we doing? If they're both the same, then we're dividing by 0. And that's basically a no-no, isn't it, in mathematics? We can't divide by 0. As soon as we divide by 0, we run into trouble. It does not exist. Therefore, it does not exist, which kind of makes sense because really what we're saying is in order to work out a gradient, you need at least 2 points. And if I'm saying both those points are in fact the same point, then of course it's not going to work. Okay, so this is the problem. And what differential calculus lets us do is it allows us to, instead of considering putting the dots on top of each other like this, what we do instead is we ask ourselves, what happens if we have the points really close to each other and then examine the behavior of the gradient as these two values get closer and closer together. So when we examine the behavior of a function as it approaches a certain value, we call this limit theory. And before we go on and talk about how we can use limit theory in order to look at the gradient at a single point, I'm going to get you to do a bit of work on limits. So I'm going to switch to a new function, to a new tab here, and I'll show you a beautiful straight line function like so. It looks lovely, doesn't it? If I asked you to work out the gradient of that function, I reckon you could do it. You could just go rise over run, so it would be a rise of 2 for a run of 2. So it would have a gradient of 1. And if I asked you to evaluate this function at any point, you could read it off this graph, right? So if I said, what is the value of y when x equals 6? You could say, well, when x equals 6, y equals 4. If I asked you to find out the y-intercept, you'd say, well, that's when x equals 0, y is equal to negative 2, so that's the y-intercept, all good. And if I asked you to find the x-intercept, you'd be probably saying that when x equals 2, y is equal to 0, because it clearly is 0 here. But let's have a look at that point if I zoom up on it. Still looks pretty good, doesn't it? Look at the y-axis here. We're now in 0.01 increments here. Now we're in 0.001 increments, and still lovely straight line. Still moving in 0.00001, so really getting quite small. I'm going to keep on going. Oh, look at this. So as I keep zooming in, the function starts to go weird. It's like a Doppler effect or something here at x equals 2. And the reason why is pretty simple. The function is not actually defined at x equals 2. It looks like it is when you zoom all the way out, but I've had to go to, that's like 1 point and then 7 zeros, 1. I've had to go in that zoomy so you can see it, but there is definitely a hole in this graph. And this funny Doppler effect thing is really looks like this because Desmos can't handle this. This is the best way it can handle this hole in the graph. So this function is not continuous. It works up to x equals 2, and then it works after x equals 2, but at x equals 2, it goes weird. And the reason why it goes weird is because of the function itself. Have a look at it. F of x equals x squared minus 4x plus 4 over x minus 2. When you have a look at the denominator here, which is x minus 2, you can see that if I set x equal to 2, then I would have 2 minus 2 on the bottom, which is 0. So you can't divide by 0, so therefore the function is not defined at that point. But why is it giving me a straight line like this? I mean, it looks complicated. It's a quadratic on the top and a linear on the bottom. Why is it giving me a nice straight line graph? Well, have a look at this function here. Have a think about how you might simplify this right-hand side. Pause the video and do that simplification, and then come back to me, and then maybe you might be able to put a few things together. Hopefully you did that simplification. Maybe you couldn't work it out, but I hope you could. The top of that fraction is a perfect square. We've got x squared, we've got 2 squared here, and we've got minus 2 times x in the middle. So this is in fact x minus 2 squared, but I might write it like this for what might be an obvious reason in a second, over x minus 2. And therefore I can cancel down the x minus 2 here, and I get x minus 2. And you'd think that's what that graph is, right? If I look at the graph again, you can see that it's a graph of y equals x minus 2. I can actually draw it here, y equals x minus 2. And it's a different color. I'll just change it to a different color so you can sort of see it. There's that function here, and there's that function here. But if I zoom up, I won't do it because it's takes a while to do. But if I did zoom up, the red one would not be defined at x equals 2, but the blue one would just shoot through that. Okay, because it's basically this one is a continuous function. There are no holes in it, but this is non-continuous. So even though the graph looks the same, unfortunately, it is not the same because of the way it's been expressed. You'd have to literally, to be fair, you'd literally have to define this function by saying x can't equal 2, okay? Because of the denominator problem. So it's not the same function. Y equals x minus 2 is a continuous function. It's defined everywhere for every value of x. Y equals x squared minus 2x plus 4 all over x minus 2 is defined everywhere except for x equals 2. So how do we evaluate this function? This is what gets us into limits territory. Because although we can't evaluate the function at x equals 2, we can look at the behavior of the function as it approaches 2. One way we could do that is by putting in closer and closer and closer values of 2, like 1.9, and then 1.95, then 1.98, and then 1.99, and all of those would see this function heading towards 0. However, limit theory allows us to be a little bit more tricky, or a little bit more clever, I suppose, with working this out. So what we can do is we can say, rather than saying what is y when x equals 2, because the answer is it's not defined, we can say what is y, what is the limit of the function? What value is this function reaching? That's what this means. Lim, short for limit, x arrow 2, to show that it is the value of x is approaching 2, and you then have the function x squared minus 2x plus 4 over x minus 2. Now, if I now set x equal to 2, we know that we're going to end up with trouble here, because we're going to have a division by 0 like I discussed before. However, if instead I can manipulate my equation so that the denominator disappears, and I can do that because I haven't set x equal to 2 yet. I can do that. I will get the limit as x approaches 2 of x minus 2. Once it's safe for me to safely got rid of the denominator in this instance, so I've got rid of the x minus 2 by cancelling out. Once I've done that, I can now safely move the value of x to 2. So I literally replace x with 2 now, which is equal to 0. Okay, so really important to see here that I'm not saying when x equals 2, y equals 0. I'm saying as x approaches 2, the value of y approaches 0. And in fact, because I'm doing this on an infinitely small scale, there is no gap between a value approaching 2 and where it is at 2. So this is the complex kind of conceptual difficulty, which, for all intents and purposes, it's okay if you don't quite get there. But what I'm doing is I'm finding a value that the y function will approach as x gets closer and closer and closer to 2, so that there's effectively no gap between the value of x. It's something that's just approaching 2, and then the value of y, which in this case is 0. So what you're going to do now is you're going to go to your textbook, and you are going to go to exercise 17F, question 1. So if I just go there quickly now, you'll see that you've got these questions here. Don't worry about the left and right limits and all this kind of stuff. We're just going to go to exercise 17F, and you're going to do this set of questions here. In almost all cases, what you'll be doing is you'll be seeing if the function exists at a particular point, and if it does, you can effectively just say the answer. So, for example, this one here, as x approaches 6, what is this whole expression going to approach? Well, it's going to be 6 minus 5, which equals 1. There's no dramas there at all. It works. X minus 5 is continuous, and so the limit at as x approaches 6 is just the same as when x equals 6. So 6 minus 5 is 1. But then you're going to have other ones like this where there is a discontinuity. So there is a discontinuity at t equals -1, because that would give me a fraction divided by 0. And so in the case of these kinds of problems, you're going to have to use your algebra skills to factorize, eliminate the denominator, and then replace t or x or whatever it is with the value it's trying to approach, and then you work out the value. And whatever value you get is what the function, this bit here, is approaching as t or x or whatever approaches this number. Hope that makes sense. So have a go at doing these, and then when we return, I will show you how this works with our gradients.